Okay, thanks, Ben. So I have the honor of being the first person to fall off the invisible step here. I hope I'm also the last. This week we'll have a number of talks on Bayesian hierarchical models. So I'll start by introducing them in the context of weak lensing and also photo-Zs, and those are in a sense coupled because in a full Bayesian hierarchical model of weak lensing, one would also include photometric redshifts as part of the model. Just to set the scene, just the approach that we're beginning to take with weak lensing is to get away from using summary statistics like correlation functions or pseudo-CLs, and to try to build a full data model for the things that we measure. And the main reason is that as we get to the era of accurate cosmology, then one starts to begin to worry about what are the distributions of the summary statistics that we're using. It's very typical to assume that they're Gaussian distributed, and then the question is, what is the right covariance matrix, and how do you get that? But there's a more fundamental question, which is really, are these quantities that we deal with Gaussian distributed? And then you may be working with thousands and thousands of summary statistics, and to assume that the joint distribution of all of those things is Gaussian is a fairly large step to take. So there's an alternative, which is to try to build the model of the data from the ground up, as it were, and this is where the Bayesian hierarchical models can be helpful. It's quite ambitious and not necessarily computationally easy. But it does mean that in principle, you can use all of the information that's in the data, and you're not restricted necessarily just to two-point statistics or some subset. So let me just describe how it would work for weak lensing. The full data model involves variability at a number of stages. For example, going from the power spectrum to the spherical harmonic coefficients is basically a random realization of the universe. The shape measurement is a very noisy it's a noisy process, so there is some variability that's involved there. But also the relationship between the shapes of the galaxies, which is what you measure, and the shear, which is the underlying distortion pattern, that is also very noisy because of shape noise. So these are some of the places, including one more actually, the redshifts are not determined spectroscopically, so there is some uncertainty in where the galaxies are. So when you build a data model, then there's variability that occurs at many, many different stages, and trying to include all of these and to propagate the errors that arise from each stage to the final result is not a trivial task. But using BHMs, then you can add in many systematic effects as well, such as the uncertain redshift distributions. The mask is very easy. If you have masked pixels, then you basically just give them infinite variance in the model, so that even with a complicated mask like the one that you see there for CFHT lens, it's a mask like that, which would be challenging for some other methods based on the power spectrum, is very, very easy to include in this. You basically just give an infinite variance to every unobserved pixel. And really, if you want to take a principled Bayesian perspective, then if you can do this, if you can approach the problem in this way, then it is really the principled way to do it. So if it's technically possible, then it's worth trying. So let me just describe a very simplified BHM for lensing. And I'll show how it can be complicated later on. The goal of all of this is always, from a Bayesian perspective, is always the posterior. So if you have if one's talking about inference of model parameters, theta, say, then the goal, the final aim, is to get the probability of theta given the data d. And for lensing, and we'll see in similar cases later on for large-scale structure, then the way that one can break this down is to introduce a large number of latent variables, which are the the true shear map. So one measures an estimated shear map, which is very noisy, and there's some underlying truth there, which is the true shear map. And if you pixelize that with some pixelization, then the values of the shear map in the true shear map in the pixels on the sky introduces a whole set of parameters into the data model. So let's just see how this works. This would be a sort of very simplified example of some of the hierarchical models that you'll hear about later in the week as well. The posterior we can compute by marginalizing over this true underlying distortion map, S, and just simply using Bayes' theorem, we can then split this up into various ingredients, the probability of the noisy data given the true shear map and the parameters times a prior on these things. And then we can again use the rules of probability to split this up again, and this exposes essentially how these hierarchical models work, because this one splits up, if this is just simply measurement error or shape noise, then this is essentially independent of the cosmological parameters and only depends on the underlying shear map. And this one is basically the theory. So this is measurement. This is theory. What's the probability of getting a particular shear map given some cosmological parameters? And in our case at the moment, we have Gaussian priors for this, but this is something that in principle you can upgrade with some of the more sophisticated techniques that you'll hear about later by doing full evolution of the mass field. And then a prior. So it splits up into these levels of the hierarchy, and if you know what these conditional distributions are, then in principle you can calculate this integral. But it's not necessarily easy, and the main one is that once you introduce the pixelized true maps, then that is a very large number of latent parameters in the model. So typically for the cases that we look at, we're talking about something like 1 million latent variables. So we're having to do integrals or explore sample from very high dimensional spaces. And that becomes rather challenging to sample from, and there's a couple of techniques which one can employ either Hamiltonian Monte Carlo, which is probably the natural one to choose, or given some restrictions, you can also use Gibbs sampling. So here's an example done with simulated data by my former student, Justin Alsing. So here, just to illustrate, this is a simulated shear map. This is one component, the so-called gamma 1 component, which is then has noise added to it, and it has a simple mask added to it as well. And the third panel will show a movie made of some of the samples drawn from, in this case, a Gibbs sampling of the true underlying field. This example has 2 tomographic bins, so you can have a look at one or the other. So these are the samples. It's of the true field. In this case, also the cosmology is also being sampled from simultaneously. So each sample has not necessarily the same cosmology, but you can see that this is some of the features in here are quite persistent and correspond to these real features. And this selection of samples that comes out of it is basically the logical outcome of the experiment. That posterior probability contains everything that you've learnt in the experiment. So you can look at the power spectrum that comes out of this. This is the E mode for the two tomographic bins, and the cross E mode. And the truth is the red line, and the range of samples gives you the uncertainties. You also calculate the posteriors for all sorts of things. We have a very high multidimensional posterior. You can process it, post-process it in whatever way you like. So these are some of the posteriors for some of the power spectrum coefficients. So one sees that they're not particularly Gaussian. So if one measured, say, a pseudo-CL for something like this, these are not pseudo-CLs, but this perhaps gives an indication that maybe summary statistics would not necessarily be Gaussian, and one might be a bit reluctant to use them.
You can also apply it to data. This is just a proof of concept with the CFHT lens survey. So these are some of the maps. This is the mean convergence maps from the 4 fields. So we get a joint distribution of the maps and the cosmological parameters. And if you're interested in map making, then you have a lot of samples of the map. You can marginalize over the cosmology. If you then take the mean, then this is what you get. The mean may not be the thing that you really want in the end, but you can get it. You can also marginalize over the maps to get the cosmology. So these are the power spectra. This is in the more familiar omega matter sigma 8 plane. You can do this with parameters as well. So this can be built into a more complicated model, and there's a number of people, mostly at Imperial, who are working on doing this for lensing. That can include, for example, at the CCD pixel level, including the PSF and instrumental noise. So propagating the uncertainties in the pixel measurement of the shape into the model. So the one I showed you was the middle section of this, but on this side we also have the galaxy characteristics, which would be include the uncertainties in the photometric redshifts as well. And I'll talk a little bit about that in the remainder of the talk. So this is quite a complicated data model to build. I'm not sure that it's the right one to build, in the sense that my feeling is that the left-hand side of this at the pixel level probably makes it too expensive with too little return. I think that one can probably characterize the shapes, the distribution of shapes, with a couple of summary statistics on an individual galaxy basis, and that is probably adequate. And the extra computational expense of trying to sample at the pixel level and the cosmology and the map is probably not worth doing. It may not be possible to do it, and I don't think we lose very much by using summary statistics for the shapes that come out. The photometric redshifts, on the other hand, I think is a very different story, because those, I think, are a very significant source of uncertainty in the process. So we're working on building these into the model at least. So let me turn to photometric redshifts. I'm not going to talk generally about the problem of getting photometric redshifts, but one specific problem which is focused largely on LSST, and this is the problem of getting photometric redshifts of blended sources. And about 40% of LSST sources will be blended. Many of them one will be able to identify clearly as blends, but some of them will be blended, but it will not be obvious from the shape information. So this is another example of using a BHM to determine the redshifts of blended sources. Now, if we can get probabilities for the redshifts of blended sources, then you could include those in some cosmological analysis into lensing or many other places. So how do we handle these probabilistically? What we're after here would be the joint distribution of the redshifts of blended sources given the data. And I'm just going to use color data, so no CCD pixel information, no morphology information. We'll go into this, but just what can you learn from the colors, broadband colors, or broadband fluxes to be more precise, about the redshifts of the components. So this is a summary of a paper that my student Dan Jones wrote and put on the archive recently. That's the only picture I have of him. So you'll notice he looks very similar to George Kyriakou, who was on the previous slide. So let me just to set the scene, let me review how this is done with single sources, and just a very brief review of the Bayesian photometric redshift method of Benitez from 2000, just to basically to introduce some of the notation and show you how the more complicated case works with blends. So the goal of BPZ is to get a posterior probability for the redshifts given the fluxes, the estimated fluxes f hat. And with template methods, then the procedure is to marginalize over the templates. So BPZ, the default set of templates, is a rather small set, and those are marginalized over. And the effect that one is looking for, as you're aware, is a redshift which shifts things to the right, but we also shift the templates up and down because of the brightness of the source, put them through various bands, and the flux data are these the data in these handful of bands that are observed. So we marginalize over the templates, but we also marginalize over the true fluxes. So we measure estimated fluxes which have errors. So marginalizing over the true fluxes involves this integral, which we can split up using Bayes' theorem and the rules of probability in a similar way to the general Bayesian example I showed you, or the weak lensing Bayesian example I showed you before, where we have a measurement error part here, and then some, well, whether you call them priors, some conditional probability distributions on the fluxes, the templates, and the redshifts, given the templates and the fluxes. So this is more or less a slightly simplified version of how BPZ works. So what's required is a set of templates and also some priors for these distributions.
So T
yeah,
is the
T is the temp. Yeah. So the.
So you mix them. You have a sort of linear combination of.
You can do that. Yeah. Yeah. I mean, this is a general formalism that you can put in what you like for the template. So yes, typically that's linear combinations is also used. Yeah. So this is from Benitez's paper. You can see the effects of of doing this. These are the likelihoods, the probabilities of the colors given the redshifts in the templates, and you see this usual bimodality because of the misidentification of the breaks in the spectrum with this high redshift, probably spurious, but good fit from the high redshift. Once you put in the redshift distributions given a certain flux, so unless the survey is very deep, then the galaxy is much more likely to be down here than it is up here at high redshift. So once you put in the information from the magnitudes, then and then obtain the probabilities given the colors and the magnitudes, then things collapse down to the low redshifts, depending on the template used, and then marginalizing over the template gives a full posterior, which is centered at low redshifts with this small probability of something being at high redshift. So this is an example where the notion of having a posterior, which is a likelihood times a prior, sort of really rather breaks down, because once you've marginalized over the templates and the magnitudes, then this doesn't simplify in any simple way. So what about blended sources? So the complications are that you have more than one redshift to infer. You also have some true fluxes, so those are the latent variables, and those true fluxes are no longer closely tied to the observed flux. So for high signal to noise measurements, then obviously with a single source, then the true flux is not going to stray very far away from the observed flux. But here we have two components, so that flux can be divided in some arbitrary way between the two components. So only the sum is well constrained. And also we don't know how many sources there are. So there may be more than one or only one. So for the time being, let's just fix n, and we can use the Bayesian techniques to infer the value of n from using model comparison techniques. So in the same way, you marginalize over a set of templates. So this is essentially, we now want to obtain a posterior for the set of redshifts of the components in an object and the set of magnitudes as well, given the observed fluxes and the number of sources. So in a similar way, we marginalize over the templates and apply Bayes and factorize the likelihood. So the reason for doing BPZ is that I don't really want to explain this, but this is basically this similar sort of subdivision. You'll notice that it depends here on the probability of the set of redshifts given the templates and the magnitudes. And here one has to be a little bit careful because the joint distribution of the redshifts won't be factorizable because of clustering. So that's a subtlety. So the natural output of this will be samples of the redshifts and the magnitudes of the component objects. And if we're interested in the redshifts, then one would marginalize over the magnitudes. So the new elements that are introduced by blending are that, as I mentioned, the redshifts are not independent because of clustering. This turns out to be a very small effect, and I think we can ignore it. Just from numerical experiments, that it seems that it including or not including the clustering makes almost no difference. The radial distribution, I think, is typically so broad. Another complication is that, unlike in the single source case, the priors for the components need to be specified to well below the flux limit. For a single source, then the chances of it being well below the flux limit and bumped up by noise are very small. But here, we don't know what the fluxes of the individual components are, and one of them may be very small. So you need to specify priors on the magnitudes that go well below the flux limit. The next complication is that the situation is evidently degenerate. You can swap the components round. So we have to do something, apply some sorting condition to interpret the results, which you can either do on magnitude or on redshift. The other complication is that we don't a priori know how many components there are, but one can either use the statistics to infer and do a model selection and decide how many components there are, or else you can marginalize over it and include all possibilities. So also we need a prior for n. So what we've done so far is just to have a uniform prior on n, but it comes in as a purely multiplicative thing, so a different prior can easily be used. And if you have some other information, say from morphology, then that may well motivate you to introduce a prior, or indeed even a delta function, to say I will fix a certain number of components because I have some image data that can be used. And if that part of the process is not using the flux information, but is using morphological information only, then the two become independent, and then you can include the information trivially. So let's go through some of these complications. So the sorting condition, here's an example from a simulated blended source where there are, as there have to be, two degenerate solutions, and then by simply defining one of the components as being the lower redshift and one of them as being the higher redshift, one can then just simply decide which of these peaks. If you just marginalize without doing that, then you're bound to get a double peak in the posterior, which is not very useful. So here's some tests on simulated data. So this is using original BPZ templates. There's not very many, so as probably some people know, the performance of these templates is not all that great, even for single sources. But the formalism allows you to choose whatever set of templates you like. So using these and some LSST-like filters and drawing some objects from priors, we then sample redshifts and true fluxes using multinest. You could use a different sampler if you prefer. Multinest has the advantage that we also get the Bayesian evidence out, so we can infer the number of components in the same step. But there's, if you wanted to use a different sampler, you could do the evidence a different way. Okay. So here's some examples from simulations with two blends. So here is these are the point estimates of the redshift. not necessarily what I would recommend using, but you have much more information. You have full posterior on the redshift. But for illustration, if you take the maximum of the posterior and plot this against the truth, then this is what you get. The blue points here are the ones which in the pair, which is the lower redshift, and green is the higher redshift. And in the second panel over here, these are coloured by whether the algorithm thinks there's one source or two. So these are all double sources, but for some of them the flux ratio is very large, and the data don't support a second component. So there's a slight Occam's razor that comes into this. So if it doesn't feel that there's a necessity to include a second component, if it's very faint, then it will prefer a single component. So those are the red ones here. This looks fairly ratty, but there's quite a lot of points in here. If you plot contours, then it looks better. So there's a lot of points along the diagonal, which is not so apparent here. The other advantage of having the full posterior is that you have some quality, if you like, of some notion of the quality of the inference. So if you restrict yourself to the sources for which you have a relatively precise measurement of the redshift, and you know that, so if you exclude everything where the RMS in the posterior is more than 0.2, then this cleans out the outliers. So these outliers are ones where, in fact, the posterior is extremely broad. And since you have the full posterior, you can use that information to cut back on the sources, and that reduces the scatter in the variation in Z over 1 plus Z by about a factor of 2. So here's some examples of easy cases and difficult cases. I mean, this is clearly a more difficult problem than just inferring the redshifts of a single source. So here's an example where there's a unimodal posterior which has identified everything perfectly well. But there are more challenging cases where you get these degeneracies like this. So this is a good example. This is a bad example, but this is really just the nature of the problem, that if you have a source which is made up of a rather faint component and a rather relatively bright component, then it may be challenging to determine both. Okay, so how can we use the evidence to infer the number of sources? Well, we just calculate the Bayes factor for, in fact, any number of components. We've focused only on 1 and 2, but with a prior, which, as I say, we take as being uniform in the number, and you can change that if you have some reason to believe that the probability of it being a single source is larger than a double, then you can change that easily. So here you see that if you just do a simple cut where you say if the evidence says that it's more probable that it's a single source, you classify it as a single source, then you get about 80% of them, about 90% of them correct. If you want to be a bit more cautious, you can put a cut in the evidence, not at 0, but demand that the evidence is significantly in favor of one or the other. And if you do that, then you get some distribution of ambiguous sources that are shown by this line here, and so the number of single sources goes down, but the number of ambiguous ones goes up. So we've also tested this on real data from Gamma. So Gamma has a catalogue of blended sources, so we can see how well it does on this. Now, the blended sources don't correspond necessarily very well with the BPZ templates, so you get quite a lot of scatter. So this is much more scattered than the simulated case, and even in this diagram here, it still doesn't look all that wonderful. But if you do this for single sources with these templates, you get something that looks very similar. So this is not, I think, a failure of the model. This is a failure of the templates, and with a better set of templates, this would look much better. So here's a similar diagram showing the number of sources that are identified. And you have to, in order to remove, so these are all double sources, spectroscopically determined. If you put you have to put the threshold in the Bayes factor really quite high before you remove all of the ones that it thinks of as being single. So there's an interesting case which we've been looking at recently, which is to say, all right, what happens if not all of your flux bands are blended? And this is, I think, quite an interesting case, particularly concerning the synergy between space-based and ground-based data. So for Euclid, there's a certain number of bands. There's a wide visible band and some infrared bands with very high resolution, but it requires the optical bands to get the photometric redshift. So what happens if you combine LSST photometry with Euclid? Well, a typical situation, or for some sources at least, you'll have sources which are resolved in Euclid but not resolved in LSST. So Euclid's resolution is very high. It has these infrared bands plus the wide optical band. LSST is much deeper but has much poorer seeing. But the combination of the two, in some cases, is going to give you resolved images in the Euclid bands and unresolved images in the LSST bands. So you can use that information very effectively, it turns out. So these are preliminary results that these will evolve slightly because one of the priors that we're using in here is not bad, but it's not quite right. So these are preliminary, but I think the conclusions will still remain the same. That if you look at objects with LSST type photometry on their own, then because you don't have the infrared bands and you have a finite number of filters, then you have some outliers out here. For Euclid, it's the bands in some ways are worse on their own, but the combination really cleans things up extremely well. So here we've lost the freedom that we would have with the LSST bands of being able to move flux from one component to the other. It's in some bands those fluxes are essentially fixed, and that really helps because that really removes the amount of freedom that you have. So the combination is really very powerful, and here we haven't thrown out any objects. And the number of outliers goes down from 10% to 1%. So for a limited subset of sources, which in absolute terms is going to be a very large number, then the combination of these two is going to be very powerful. And it cleans up the degeneracies as well quite nicely. So here's what you would have with LSST photometry for a particular blended source, where there's a big degeneracy between two solutions, which are quite well separated. The truth is down in the bottom right-hand corner of this panel. So if you've got blended sources in all bands, then this is what you get. If you then resolve the fluxes in some of the bands, in the Euclid bands, then this is what you get. And this is, the scales here are very different from here, but it's basically just lifting this degeneracy completely and simply picking out the true combination down here. So this algorithm is available as software, which Dan has written, called BlendZ, and you can choose your own priors and your own templates, and maybe use a better set than the ones that we've used for this exercise. So it's easy to install, and it's quite well documented as well. So it's written in Python. It's not particularly fast. If anybody thinks it would be useful to rewrite it in a faster code, then that would be interesting to know. So let me just summarize by saying that these Bayesian hierarchical models are a very powerful methodology for doing the scientific inference in a number of areas, and if you can do it, I think it is the thing to do. It's the weak lensing example is much easier than galaxy clustering because of the absence of having to deal with bias, galaxy bias. It's more complex in that it's a spin 2 field, so one has to deal with more power spectra, E mode and B mode, and the cross terms. For all of these things, you need to know the probability distributions, the conditional probability distributions, and in the redshift part of that, then there is a Bayesian method, and Boris and Daniel and Hiranya have worked on that, also Alex Maltz, for how one can incorporate that into a model like this. And as I've just shown, you can also generalize this to blended sources in a probabilistic way. Okay, I'll stop there.